In this short module, we will discuss numerical solution of Laplace's equation. We have already seen analytical solution of Laplace's and Poisson's equation. This numerical solution can be like it can actually supplement most analytical solutions. You can visualize them, but in a more practical scenario, you will be using a lot of numerical methods to solve electromagnetic problems such as Laplace's equation, Poisson's equation, wave equation, waves on the transmission line or waveguide. These numerical solutions or numerical techniques are a subject of deep interest because most problems in electromagnetics are not or cannot be solved simply by analytical means. There are a lot of numerical techniques that one can talk about, but in this short module I will only discuss a simple numerical technique known as finite difference method for solving Laplace's equation in its most simplistic setting possible. Okay, the two-dimensional Laplace equation is what we are going to solve numerically by using the finite difference method, but you should remember that there are a lot of numerical techniques, and these techniques are required because real electromagnetic problems are quite hard to be always amenable for an analytical solution. With that background for why numerical methods is necessary, let us jump right into the Laplace equation, numerical solution of Laplace's equation, by first looking at what Laplace's equation is. Of course, we already know that for the wave which is for the situation where you have a potential function V that needs to be calculated, the Laplace's equation allows you to do so. So, del square V of x comma y, I am going to work in the rectangular coordinates. It can, of course, you can work, of course, Laplace equation in any other coordinate systems. The formulation changes only slightly, the formulas will change slightly, the basic ideas would remain the same. So, let us say I want to solve this Laplace equation del square V of x y equal to 0. Obviously, this is 0, but if it is 0 everywhere, then there is a trivial solution for V. So, clearly this is 0 only in the interior points. On the boundary there are specific values of the potential V. This is true because you will actually have physical electrodes placed and you are applying the potential differences that would create an electric field between the regions constrained by the electrode. So, you have an electrode, let us say here you have one more electrode, you have one more electrode, and you have one more electrode with a certain gap here. These electrodes can be electrodes or they could be simply conductors, okay, and then you apply a certain potential here. So, maybe this is a time varying potential that you have applied. This will create a time varying electric field inside this region, which can be obtained by first knowing the potential function, okay, and then solving for this particular equation. So, once I know what is the potential function, then I can go back and solve for the electric field. Of course, this is actually not time dependent. No, I mean, for these formulations we do not normally go for time dependent formulation in this manner what I am describing. It is possible to solve this for time dependent, but the formulation is slightly different. So, let us not complicate our life. So, I have this as a certain potential that I have applied. Okay. So, I will consider the simplest possible situation. I will label this as the y axis, this as the x axis, and let me define a certain, let me define the problem consisting of this grid. A small gap is required, okay, physically, but we will not really worry about that gap in the formulation. So, this is the grid, or the if this is a tubular structure, you can think of this as a tube, and then I am looking at the cross section of the tube. Okay. Let me also specify the values of the potentials at the boundary. Let us say these three values are 0, and for simplicity let me put the value of 1 over here. Now, how do I go about solving numerically? Well, computers cannot work with real variables x and real variables y. There is a finite range of numbers which is determined by the word size of the computer. It could be 32-bit computer or a 64-bit computer. Depending on that, there is a certain range of numbers. This range is quite large, but it is not enough for us to consider that the entire real number line can be implemented on a computer. So, computers do not take in continuous values. They have to, the values that you are using must be discretized. So, the first step in solving Laplace's equation numerically would be to define a grid or a stencil. Sometimes these words are used interchangeably. I prefer to use the word grid. So, what is this grid? It basically consists of considering certain points alone, okay, forming a grid. Okay. So, these are formed by the points. Let me try to use a different color here. So, this is one point, this is another, 3, 4, right. So, these are the other points that I have. So, please note the points that I am calculating here. Okay. Now, this is a grid that we have plotted, which means that on a computer, since I do not have all the values of x. So, between these two grid points I do not have enough, I mean I do not have the ability, or the computer does not have the ability to represent all these points. So, the computer recognizes only the points that I have shown on this grid. Now, you can see that these grid points can be separated nicely into two groups, right. On this line where at the edge of the grid or at the boundary, the points all lie on the boundary. So, the outer grid points are all the boundary points, okay, with a specific values of the boundary values that are given in the problem itself. So, these are the grid points, these are called as the end point or the boundary grid points, or sometimes called the exterior points, and there are certain grid points sitting inside. Okay. So, these grid points are called as the interior points. Okay. These are called as the interior points, or these are the interior grid points, and this is how you actually create a grid. This is not the only way to create a grid. You can actually create a grid that would look triangular, okay, that could look skewed situation. So, let me try and put the skewed grid here. So, this is a skewed grid, right. A rectangular grid is the one that we have constructed. So, this is my rectangular grid. You can also have circular grids, okay. So, you can have circular grids cut at different angles, okay. So, this is one circular grid. You can have triangular grid, this is an example, a slight example of a triangular grid, wherein you are defining the grid points in a triangular way. So, these different grids are used for approximating the continuous range. So, in this case it is easy for me to consider the rectangular grid. If I were to use a circular grid, I will be missing out some of the regions of interest. So, depending on what the shape of your problem is, you might have to consider different grids, and the performance of the numerical technique depends on the grid size, the type of grid that you have used, and the number of grid points that you actually take, which is again connected to the size of the grid. Okay. The general thing is that try large number of grid points to get better or accurate results. You have to take this advice also with a pinch of salt, because there are situations where you can increase the grid size, but you do not actually get improved accuracy in the solution. So, first step is to create grid. Okay. We have assumed a grid. This grid will now have 2 points, the interior and the boundary points. On the boundary, I already know the values of the potential, because that is the problem statement, right. If I do not know the boundary values, then well, this would be a boundary value problem. So, I know the boundary values or the values of the grid points at the edge or the boundary. I do not know the interior grid point values, and this is what I want to calculate from numerically solving. So, what would be the second step? Well, the second step would be to discretize del square V of x y. Okay. This equation I need to discretize. Again, before going to this discretization, I need to know how this V of x y itself can be represented. These are the grid points, as I have told you. Let us label these grid points by, so I have an x which is going from, so I have cut 4 planes, right, along x. This is one plane, second plane, third plane, and fourth plane. Let us say the values of x are 0, and so let us label this as x0, x1, x2 and x3. These are the 4 points that I have created. This could be, for example, x equal to 0 and x3 equal to 1, if that was your case, and these are now 4 points along that. Similarly, for y, I will have 4 points, y0, y1, y2 and y3. Okay. Now, every point on the grid can be represented by a 2-dimensional array, right. So, I mean the entire grid point can be represented in a 2-dimensional array, where x takes on values of x0 plus I into h, h being the separation between the grid points, right. So, h is x1 minus x0 or x2 minus x1 or x3 minus x2. We will assume uniform grid spacing, which means that h is constant for all this, and I will go from 0, I will take on values I equal to 0, 1, 2 and 3. So, I have generated all the 4 points, with x3 being given by x0 plus 3 into h, right. So, this is h, 2h, 3h. So, 3h plus x0 will give me x3. Okay. Similarly, y variables are actually on the computer. So, this is the continuous, and these are the computer representations of x values. Okay. So, y will be y0 plus jh, and j again takes on values of 0, 1, 2 and 3 in this particular example. Okay. Depending on the number of grid points, this will be m, this will be n. So, the total grid size would be m cross n array. Any point inside that can be represented by v of I comma j, where I would represent the ith point. So, it would be I equal to 0, I equal to 3 would be the last point. This is kind of the C notation that we are looking at. For the interior case, I is equal to 1 and 2, j is equal to 1 and 2. So, this would be the interior situation, right. The exterior points are all with I equal to 0 or j equal to 0, and I mean these are the outer layer points that we are considering when I and j are having at least one of those elements will be equal to 0. So, the first step is to grid, and once you have grid, you have defined a grid, x and y will now become discrete values or discrete variables taking on these values which I have shown here, with x0, y0 being the origin point, okay. And you can refer to the value of the potential at any point on the grid, whether it is boundary or in the interior, by writing this as v of ij, where I and j can take on the values of 0 to 3, 0 to 3. This is a symmetric grid that we have chosen, okay. Now, the second step is to discretize this del square v of x comma y equal to 0. Now, what do I mean by del square v? Let us expand that. Del square v is actually del square by del x square of v plus del square by del y square of v, okay. Now, this seems to indicate that if v of x y is the potential function, then del square v by del x square is the partial derivative, is actually the second partial derivative when y is taken to be a constant, okay. In terms of our grid, what it means is that if I take the x equal to y equal to constant plane, let us say y is equal to y0 plane, how would my v of x y vary along this grid when y is held constant is given by del square v by del x square. Similarly, if I take an x equal to constant plane, let us say x equal to x2 plane I take, then x2 value is fixed, whatever the value, x2 is equal to x0 plus 2h, that is fixed, but then how does v of x y change, or with respect to y is given by del square v by del y square. So, clearly I need to represent this del square v by del x square and del square v by del y square, which are both continuous quantities on a computer. How do I do that? Let us take the first, I mean let us take the simplest case of the single variable v of x, okay. Let us assume that v of x is some function. Then if this function has a certain form which is continuous function, let us say I pick a point x0, okay. If I pick a point x0 and an additional point x0 plus h and one point to the left have x0 minus h, then what I am trying to find by v of dv by dx is that dv by dx, okay, is actually the slope of this one at the point x0, okay. This slope can be obtained in two different ways. So, dv by dx can be written as v of x0 plus h minus v of x0 divided by h, okay. This would be, this is called as the forward difference formula. This can also be written as v of x0 minus v of x0 minus h divided by h. In the classes on mathematics, you would have seen that this limit of h must be tending to 0, but on a computer I cannot tend h to 0 without really blowing up the problem in a very complicated ways. So, I have h which is fixed, it is small, but it is not really going to 0, okay. So, this is called as the backward difference formula. Both formulas appear with an error of h, that is the order of h. So, improve h, to reduce the error you need to make h smaller. These are fairly bad ways of evaluating the derivative. A slightly different way which gives you an error of the order h square is known as the central difference formula, which is obtained by appropriately adding these two terms, right. So, this is dv by dx, this is also dv by dx. If I subtract these two, so this is dv by dx which is evaluated at this point. If I have the same dv by dx which is v of x0 minus v of x0 minus h, actually by manipulating these two, let me not go into the details of the manipulation. If you do that, then dv by dx can be approximated as v of x0 plus h plus v of x0 minus h minus 2 into v of x0 divided by h square, okay. To do this you need to use Taylor series and then expand this appropriately. Let us not do that one at this point. So, I am not going to do this thing, but it is you guys can actually verify this, okay. There is a 2 in the denominator or not, I am really not sure, but that is really immaterial at this point. So, I have dv by dx as this part, but this is not what I want. What I want is d square v by dx square. How do I obtain d square v by dx square? Well, I remember that this is nothing but d by dx of dv by dx itself. Okay. Now, since I need an evaluation with respect to point h, right. So, I will consider x 0 minus h by 2 and x 0 plus h by 2. I will find out what is dv by dx at these 2 points and then take the difference. Here I won't do the central difference, I will do a single difference, and when I do that I will be able to obtain the expression for d square v by dx square, and that expression will be given by, so this d square v by dx square is given by, in the numerical way is given by v of x 0 plus h minus 2 v of x 0, okay, plus v of x minus, sorry, x 0 minus h divided by h square. Well, this seems to be in the same vein that we have obtained, and that is right. So, this you need to remember that this central difference formula, but this is actually the formula for d square v by dx square as well. Okay. This has an error of h. Okay. So, let us get back here. So, this is your d square v by dx square which we have obtained numerically, but again you might say that that is not what I want. What I want is del square v by del x square. Well, the solution is that in this expression I have assumed y is equal to constant, right, which means that I have held j as a constant value, and this is really the changes in I that I am looking for. That is, if I hold the y equal to 0 plane, which would be horizontal, and I am looking at how v changes with respect to x, that is what I have obtained. So, this del square v by del x square is given by v of I plus 1 comma j. So, now notice that I am actually referring to the I plus 1th point on the j equal to constant value minus 2 v of I comma j plus v of I minus 1 comma j, right. This would be going along the y equal to constant plane divided by h square. Similarly, del square v by del y square will be equal to v of I comma j plus 1 minus 2 v of I comma j plus v of I comma j minus 1 divided by h square. If I add these two and then take the result equal to 0, that would be the numerical approximation or discretization of the Laplace's equation. So, Laplace's equation del square v equal to 0 becomes on a computer v of I plus 1 comma j minus 2 v of I j, right, plus v of I minus 1 j, which would tell me how v is changing with respect to x. Then I have the corresponding expression for I, which would be v of I comma j plus 1 minus 2 v of I comma j plus v of I comma j minus 1 divided by h square is equal to 0. So, this is your second step. The third step is to assemble these equations, okay, to assemble these equations in matrix form. You might ask why we need to assemble equations in matrix form, and the reason is because once you put these equations in a matrix form, then you can use very powerful matrix solvers for solving the system of equations. Okay. So, you can find not only the values, but you can also find the eigen values, which are sometimes required for this Laplace equation or for other equations such as wave equations. So, you can actually find solutions to lot more interesting situations where when you assemble the equations in the matrix form. Now, you can do that for the case where I equal to 0, 1, 2, 3 and j equal to 0, 1, 2, 3. I will write down only one line of that equation, okay. And if you add these two, there will be v of ij coming in with a factor of minus 2, so that will become minus 4, and then I can push all this h square equal to 0 onto that side, okay. So, if I write down one equation, so that would be, and then change the signs of this one, so that would be 4 v of 1 comma 1. I am writing this in the interior points only. So, I am writing this in the interior points, which can be 1 1 1 2 2 1 and 2 2. So, these are the 4 interior point variables that I am looking at, and corresponding to 4 interior points I am writing the equations in here. So, this would be minus v of 0 1 minus v of 2 1 minus v of 1 0 minus v of 1 comma 2 is equal to 0. So, now there are 1 2 3 4 5. So, 1 2 3 4 5, this one I have. So, you can continue to write the equations for the other 3 interior points. I will not write it here, but you can and you should write this one, and when you write everything and put them in a proper matrix form, you can write this as sum A x equal to B, okay, where A will be this point 4 minus 1 minus 1 0 minus 1 4 0 minus 1 minus 1 0 4 minus 1 0 minus 1 minus 1 and 4. Okay. So, you can write down the equations in this fashion and then say this is V of 1 comma 1, V of 2 comma 1, you have V of 1 comma 2 and then you have V of 2 comma 2. This would be your x. So, this is x, this is A. On to the right hand side you will have V of 0 comma 1 plus V of 1 comma 0, then V of 3 comma 1 plus V of 2 comma 0, V of 0 comma 2 plus V of 1 comma 3 and then finally you have V of 3 2 plus V of 2 3. Okay. So, you can substitute for the expressions here, these two values will turn out to be 0. So, this is your B vector. So, this will turn out to be 0, this will turn out to be 0, and what is this V of 0 2? V of 0 2 point comes, if you go back to the boundary, this is 0 and 2. So, on 1 and y equal to 2. So, the value here is 0, but then there is one more term sitting here which is V of 1 comma 3, which is this interior point V of 1 and 3. So, this is 0 1 2 3, which is the point here. This is V of 1 comma 3, which is 1. Okay. So, accordingly these last two values will be equal to 1. When you solve this system of equations, you will end up with the solution for the x vector, and that would be the solution for V of x y and how it would be there in the interior points. On a MATLAB or some other package, you can then connect how V would be and obtain surface plot, or if you want to, you can obtain multiple line plots. So, to summarize, there are three main steps for numerically solving Laplace equation using finite difference method. First is to assemble, first is to define a grid, second is to discretize del square V equal to 0 expression, and finally you will assemble and solve in matrix, solve the resulting matrix equations to obtain V of x y. I would suggest that you understand this module and verify each statement that I have made and fill out this. So, I will leave this as an exercise to you and you will be able to obtain the solution. I will put up the solution in the attached note, you can see that for more details, and I hope that you will try out this simplest numerical technique to better appreciate the kind of problems that you can solve. Thank you.